All right, we're going to go through some questions here. In these questions here, they give us a set of vectors, and they want us to determine if the set of vectors is linearly independent or not, and some justification with that. So if you take a look here, if we look at our first set of vectors here, I have vector u1, u2, and u3. If this set of vectors is linearly dependent, then there must be one of these vectors, let's say u3, can be written as some scalar multiple of u1 plus another scalar multiple of u2. Or vice versa, u2 can be written again as some scalar multiple of u1 plus some scalar multiple of u3. So what we want to do here is sometimes visually you can inspect it and see whether one is a multiple of the other or a scalar multiple of the other two. So for instance here, if you do take a look and do some inspection, you'll find out that if I take vector u3 and I double vector u1 and add that to vector u2, notice that if I double this first coordinate of u1, you're going to get 2. And then we have here 2 plus 3 is going to give us the 5 that we wanted. Then if I double 0, I get 0. Add that to -1, you get -1. If I double -2, I get -4, plus 0 is -4. And last, if I double 4, I get 8, plus 2 is 10. So right away, we can see that vector u3 is actually equal to twice vector u1 plus vector u2. Right away, that shows that the set u1, u2, and u3 are linearly dependent. Now, it's not always possible to see the combination so easily. If you can't do that, another option is you can put it in a matrix here and write these column-wise, and then go through your Gauss-Jordan elimination in that I want these two coordinates to be 0. So I'm going to take row 3, and I'm going to add that to twice row 1. I'm going to take row 4 and subtract 4 times row 1. And then we want to see whether this set is going to be linearly dependent. So going through this here, you're going to get 0, 6, and this will be -4 plus 10 is 6. And this is going to give me 0, and this is going to give me 2 minus 12 is -10. And then once again, -10. And now you're going to want to do the same thing here using your Gauss-Jordan. I'm going to want to eliminate the 2 entries there I've highlighted. To do that, I'm going to take row 3 and add that to 6 times row 2. I'm going to take row 4, and I'm going to subtract that by 10 times row 2. Going through that, I end up getting here 1, 3, 5, 0, -1, -1. And here we get 0, 0, 0 for that row. And then likewise here, subtracting this up here, you're going to get 0, 0. All right, continue this up here. We can quickly see if I take row 2 here and just multiply across by -1, I can quickly make these positive. Just makes it easier to work with. I want to go ahead and I want to examine whether this is linearly independent. So I'm going to want to get a 0 in this row and in this row here. So I'm going to go ahead and take row 1. I'm going to subtract that from 3 times row 2. So going ahead and doing this operation here, I end up getting here 1, 0, 2, 0, 1, 1, 0, 0, 0, 0, 0, 0. And take a look here. Once we get to this point here, we know that I've now shown that this vector here, i.e. vector u3, I can see that it is going to be linearly dependent on the following 2 vectors because we have the combination here. It tells us twice the first vector, i.e. u2, plus the second vector is going to equal vector u3. So again, as highlighted in the lessons here, grab your columns that have your just the leading ones on the anchors here. Grab those values, and those will end up being your linearly independent vectors. So putting this together here, we can now imply that this set is linearly dependent in that the third vector here is just a scalar multiple combination of the first 2. All right, let's take a look at another. In the next example, same thing, same idea here. You want to examine whether this is linearly independent or not. We can throw this in a matrix and see if you don't want to examine the combinations, especially if the set of vectors is linearly independent. You're going to have to go through this process. So I'm going to go ahead and make that entry 0. To do that, I'll take row 3 minus row 1. And this is going to give us 0, 1, 0. And continuing up here, I'm going to want to make this entry a 0. So I'm going to take row 3, and I'm going to subtract row 2. Going through that, you get 1, 2, 0, 0, 1, 1. And this will be 0, 0, negative 1. Continuing this here, I want to go ahead and make this entry a 0. So to get rid of that, I'm going to have to take row 1 and subtract twice row 2. So this will end up giving us a 1, 0, this is going to be minus 2. And this will be 0, 1, 1, 0, 0. I'm going to go ahead and just take row 3 and multiply by a minus sign, making that a 1. And continuing up here, I now want to make this entry a 0. So I'm going to go ahead and take row 1, and I'm going to add that to twice row 3. And doing this, we end up getting 1, 0, 0, 0, 1, 1, 0, 0, 1. And the last step, finishing this off, I want to go ahead and make this entry 0. So I'm going to take row 2 minus row 3. And doing so here, you get 1, 0, 0. This will be 0, 1, 0, and 0, 0, 1. So finishing this up here, I've now shown that these 3 vectors are all linearly independent. This whole set is linearly independent vectors. So now I've shown that in this case here, the set Z1, Z2, and Z3 is a linearly independent set. All right, let's take a look at some more. So in the next set of questions here, they give you various subspaces, and they want you to determine what is the spanning set, what is the basis, and what is the dimension. So let's take a look at some of these here. We'll start off with question A here. So in question A, what they want you to find in question A is they first define the set V. They tell you that it's the collection of all vectors coming out of R2 such that that vector is a scalar multiple of the vector 1, 2. So like for some real number R, I've got the vector W is just it's a multiple of the vector 1, 2. So what we want to do here is go ahead and find the spanning set. Right away you can see this is the definition of our spanning set, because I know if W is the collection of all multiples of 1, 2, then if I were to span on the vector 1, 2, that would equal vector V. So I already know that the spanning set of, because that's the first question. In question A is what's the spanning set? You just span on the vector 1, 2. That's all multiples of 1, 2, which is exactly what vector V is defined to be. So that's your spanning set. Moving forward, they then ask, what is a basis? Well, your spanning set consists of a single vector. In itself, that vector is linearly independent. That is a basis. So your basis for this set is going to be generated from the vector 1, 2. And putting that together, the dimension of V is just the number of linearly independent vectors. Number of vectors, I guess, in your basis set, in this case, is 1. So this is an example of a one-dimensional subspace that consists of all scalar multiples of 1, 2. All right, let's take a look at B here. So for question B, same idea. It's going to be the set W, and the W is the collection of all x, y, and z values that satisfy this equation. So to satisfy this equation, if we want to solve this, we have to convert this as in scalar form. I want to convert this in terms of its direction vector, so I can kind of see what the span on those vectors is. So right away, if I were to solve this equation, I'm going to let z equal t, where t is some free parameter. Likewise, I'll have to let y equal s, where s is some other parameter. putting this together, that implies that x is going to be negative 2t plus s. So now I've got my vector x, my vector y, and my coordinates x, y, and z. Putting this together and rewriting my set, the points in W are the collection of all x, y, and z elements such that it will equal your parameter s times the vector 1, 1, 0 plus your parameter t times the vector negative 2, 0, 1. So you can see here from this expression, you can notice right away, you can see that this contains the origin, right? It's got the 0 vector in there as one of the values of W. More so, we're also can see our direction vectors. So I have one direction vector here of 1, 1, 0. I have another direction vector here of negative 2, 0, 1. So if I span on those vectors, i.e. if I take the span on the vector 1, 1, 0, and the span on the vector negative 2, 0, 1, I can see that'll generate this exact set because this is your S and T values are, in this case, all real numbers. So if I span on these vectors here, that'll generate my vector subspace here, W. So that's taken care of. I know the spanning set. Automatically, these two vectors are linearly independent together. If you put these together, these are not, I cannot write this vector as a multiple of this one or vice versa. So therefore, this is a spanning set, but is also your basis here. So the basis set is these exact vectors. And therefore, based on that, the dimension of your subspace must then be 2. And the reason for that is we have obviously 2 here. All right, let's take a look at one more. And for the following question here, we want to go ahead and interested in the all vectors x, y, z. This is 4 coordinates here that satisfy the following. So right away, we want to convert this. I want to extract out the direction vectors on this expression. So if I break this up in terms of its x, y, z values here, you have your parameter x is going to be 1, 0, 0, 1, plus you have your y parameter here is 0, 1, 0, 1. And lastly, you have your z parameter is going to be 0, 0, 1, 1. And so again, I've broken this apart. And you can see here, if I were to redistribute this in, collect this up component-wise, you would generate this exact expression. And right away, you can see here I have my one direction vector, my second direction vector, and my third direction vector. And from these, if I span on these direction vectors, you will generate, in this case here, your set U. These 3 are linearly independent from one another. And lastly, the dimension of this is 3. So in this one here, if you span on these vectors, that'll generate the subspace U. These 3 are linearly independent from one another. You can even verify this further if you want to put this in a matrix and row reduce it. You'll see they're linearly independent from one another, and also the dimension of this, in this case here, is 3. All right, that concludes today's examples here. Just going through some examples of linear independence and dependence, dimensions, and your spanning sets and basis. Thank you.